Hello, good afternoon. Thank you very much for all of you that was here with us. Today we are with Fabio Pitari from CINECA. He will present the 20th Fenix Infrastructure webinar about interactive computing services in Fenix. I'd like to let you know that this webinar will be recorded. And to get access to the Fenix services, you can access from Fenix website. And I'd like to let you know too that we have the Fenix white paper with the lessons learned in HPC service provision. So we can access all information, download the white paper from the Fenix website. I will share the link on the chat here with you. At the end of Fabio's presentation, we can leave your question in the chat. Fabio, it's your turn now. Thank you very much to be here with us.
Thank you very much, Luciana. So welcome everyone. I'm Fabio Pitari from CINECA. So I want to show you a little bit I will talk you a little bit about interactive computing. So I will start with the general concept. So what's interactive computing? Why do we care about? Why you might be interested in using it on supercomputing center, in particular on the Fenix research infrastructure. And then I will show you, first of all, the first implementation that I will show you is the one that has been developed inside Fenix, and in particular in the IC project. So this solution is up and running at CINECA. It's not publicly available yet, but it's going to be opened in a public production before the end of the month. So I will show you the details of this particular implementation. But actually, outside of the IC project, there are additional interactive computing services up and running in the other sides of the Fenix research infrastructure. So I will show you one by one very quickly the interactive computing services which are at CSCS, at JSC, at BSC, and at CEA. And I will try to enlighten the differences with respect to what I will show you about the IC implementation. So let's start from scratch. So what's the usual approach that you have when you want to access to some HPC resources? So the default, let's say, approach that the user have when he wants to run something on an HPC cluster is to access to some remote login node via SSH on a command line. This is the standard approach that you have. And from these, maybe these login nodes on the cluster, maybe you can compile your code, or you can use the already compiled code in the environment that you find in the environment. Then you want maybe to run your specific simulation with your inputs and your outputs. So you create a job script and you submit the script somehow in the scheduler, maybe Slarm or whatever is implemented in the cluster. And then you submit the job, and then basically the simulation that you want to achieve is somehow pushed inside a queue system. So you know that at some point that simulation will start and will end, but you don't know when, because there are also the users, and so you need to wait until the resources are free. And which is fine, but it's might be difficult to check, for instance, intermediate results when you submit a job, because you don't know when it starts. Everything is done via command line, so it might be a bit not the most, let's say, user-friendly approach when you want to, I don't know, visualize, for instance, with graphs, intermediate results. So there are some advantages for this approach, because it's the one which is the most used in the HPC cluster, and it's basically available everywhere. And it's the fact that basically you have quite an optimal usage of the hardware resources. So basically, as long as you have enough users, all the nodes of the cluster are employed very efficiently because they are sorry, they are all employed to run some core part of the simulation for some simulation for some user. But the disadvantage for the user, mainly for the user from the user side, is the fact that the user doesn't know when the job will start. It doesn't know if it's going wrong. Maybe there is some mistake somewhere that makes the simulation wrong, and you will realize it only maybe the day after, which might be bothering. So in the end, in practice, the user cannot change the workflow in the middle, cannot interact with the workflow. The workflow is queued somewhere and needs to go on until the end. This is the opposite idea of the interactive computing approach. So with the interactive computing approach, the idea is to have something that with a possible interaction, direct interaction with the user. So the user can interact on the fly while the code is running, and maybe check intermediate results and maybe change the direction in which the workflow is moving, which might be sorry, which might be very comfortable in the case in which maybe you are developing something, or maybe in the case in which you want to exploit different tools or explore different directions. And it's something that it's a bit difficult to achieve with the previous approach that I showed you before. So how can you obtain such results? But well, the idea is the fact that you allocate some resources, and despite the fact that you are running the job exactly in that moment, because you can access directly to that resources and run some code on that resources. And this can have very different, let's say, levels of interactivity. So the most, let's say, common one maybe is just the approach that you have on the scheduler class, on the scheduler that you find on the cluster with SSH, in which you allocate one node, and maybe you can interact with the computational resources on the node just using the command line. But actually, the very common tool that is employed in the interactive computing approaches, one of the most common one is Jupyter. Probably most of you already know Jupyter, but just in case, Jupyter is a tool which allows you to expose to the user a web interface inside your web browser. And inside this web browser, you can run your code, which can be Python code or Julia code or R code or C++, C code, whatever you want. You need to extend somehow from server side the implementation, but it can be easily done. And the execution of the code can be divided into cells. Each cells contain a fragment of code, so that you can run each fragment separately. So you can run the first part of the code, then check the results, then maybe change it and run it again, then go on and pass to the second step, in which you run another fragment of the code and maybe visualize the result in the middle. And this is achieved very easily with Jupyter because it's thought to be used like this. So it has some additional features with respect to the SSH approach, which can be actually sufficient for many other applications. But Jupyter allows you, for instance, also to have a web interface which is easily extensible with a lot of extensions that you can find around the web and also on the official website. And it's much more user-friendly because, first of all, everyone can easily access to a web browser. And in addition, inside the web browser, you have a graphical interface, so you can display, for instance, I don't know, you can plot your results in the middle very easily, and you can change your workflow accordingly to the plots. So Jupyter is a very common tool in order to be used in a interactive computing solution. This is the one employed in the IC implementation and also in JSC implementation and in the implementation at CSCS. But actually, you can also use it from the other two implementation, which I will show you later, which are the one at BSc and the one at CEA, which are a bit different because they start from SSH. And I will show you later the differences with respect to what I'm going to show you now. So summing up, there are a few services which are up and running at CINECA about interactive computing. I will start showing you with some movies the one which is up and running at CINECA. This is developed inside the IC project, but this is actually available for all the Fenix sites. So every Fenix site who wants to implement the same solution can actually access to the Ansible playbooks, which are used to deploy the solution at CINECA, and then the same service could be exposed for every partner of the Fenix project. And there are also already 4 up and running public services of interactive computing, one at Zurich, one at Barcelona, one at CSCS, and the other one at CEA. And I will show you also those implementations. So there's one thing that you need to know, how to access to these resources. I will stress it later once again, but just to let you know, in order to access to each service, the only requirement, but is a mandatory requirement, is to have an active project on that specific site. So if you want to access to any of these interactive computing services, you need to have an active project with computational resources available on one of these supercomputing centers. So let's start from the IC implementation, which is running at CINECA. This has been developed by together with the E4 company inside the IC project. And once again, is actually deployed for, developed for all the Fenix partners, not just for CINECA. And it's basically using 3 main components. There is a front-end layer, which is the one that is exposed to the web, and is the one that the user will see. Basically, it is the one that exposes the Jupyter Lab interface. We will call it front-end. Then there is a backend layer, which is basically a Jupyter server running on the cluster, which is not directly exposed on the web for security reasons. So there are some computational nodes which are dedicated to this infrastructure, which we will call them backend nodes. And they are running on they are running a server on the HPC cluster, and the connection between this Jupyter Lab interface and the code actually running on the HPC cluster is actually hidden to the user, but is actually achieved via Slarm spawner, via Slarm scheduler, sorry. So summing up, the structure is something like this. So there's a cloud environment in this case. So we installed the front end in a cloud environment for convenience. I will explain you later why. And this is the web exposed part of the infrastructure, whereas everything else is actually part of the Galileo 100 cluster in case of CINECA. But actually this is not mandatory. This could be deployed by any other Fenix partner and not just using cloud, but could be also deployed on a bare metal node. So it's not mandatory to have this connection between an HPC cluster and a cloud environment. It can be deployed with every, let's say, server client frameworks, as long as there is a scheduler in the middle which can manage this interaction. So currently, so as soon as we will open the pre-production phase for the public access, there will be, in the case of Galileo 100, there will be 18 nodes for the users, and they will be provided with the 2 NVIDIA GPUs B100. And they can be freely accessible to all the users which has computational resources on Galileo 100. either via Fenix accounts or via any CINECA account. So this part will be reserved for the interactive computing framework, but actually from these backend nodes, you can actually access also to the computational nodes via the usual batch jobs via a web interface. I will show you later. So I will not bother you too much with too many words. I will show you a couple of movies I did from my computer. So basically, the idea is like this. So you connect from your browser to a website, which is written later in the slides. And you put your credentials for the cluster. In this case, I'm putting my credential for Gaia 100 cluster. So as soon as you log in, you see a form, and in this form, you can basically choose some parameters for requesting some resources. So first of all, you will be able to choose an account in order to understand from which project you need to be, which is the active project that you have on the cluster. Then you can change the number of cores, so you can change the amount of RAM memory. Then you can also actually change the number of GPUs. For instance, in this case, in the drop-down menu, you will see that there are two. It is possible to choose until two V100 GPUs. The table that you see in the bottom tells you that there are, for instance, in this case, there are 5 available nodes with 2 GPU available, which means that basically all the nodes are free. There were just 5 nodes at the time. So basically, you have a rough idea of which are the resources available. By the way, the bottleneck for the resources is just the GPUs, because I will show you later that CPU are not a problem. I will explain you later the detail. So the idea is that now, for instance, you choose the resources that you want, you click on start in the bottom part of the page, and then your job starts. So why it tells you that CPU are not an issue here? Because basically all the CPUs of the nodes are available for all the users, but if in the unlucky case in which all the CPUs will be busy, they are given actually in oversubscription. This is done for a specific reason. It's done because when you log in inside your web interface, you don't want to wait for the allocation of the resources. This is something different with respect to, you want something different with respect to a scheduler-based system. You want to have a near immediate access to the resources. You want to start the web interface and have immediate access to the resources that you ask. So in this case, you will never need basically to wait because we have so many CPUs available that it's very unlikely that all the CPUs will be busy by other users. And if they will be all occupied by other users, there will be multiple users on the same CPUs, so sharing the same resources. So you will not be rejected from the web interface, basically. This is not the case for GPUs, actually, because if all the GPUs will be busy, you will be noticed that there are no resources available for the kind of job that you are asking, basically. So this is the interface that you see. And as you can see, it's a common Jupyter Lab interface in which you basically have some kernels. We added some default kernels. For instance, we added something about Dask, something related to TensorFlow, and something for PyTorch. But actually, these are just default choices, and the user can actually add its own custom environments. And basically, beside these basic instruments, we added some plugins that allows you to have some additional features like the Slump Queue Manager that you see at the bottom that I will show you later. And so let's start from the very basic experience. So the easiest approach that you can have is using just Python commands inside the Python notebook. So in this case, I'm running just an hello world in Python and running it. But if, for instance, you are more familiar with C++ or if your code is using C++, you can also actually use the C++ kernel, which is implemented via kernel called Xius. And in this case, basically, you can run any C or C++ code. I'm running a C just right now. And so these allow you to use basically many different kind of codes on the same platform. We will also implement Julia very soon, and there is already R available. And so this is a very basic approach that you can have, but actually, if you want to have something more complicated, you can, for instance, what I'm going to show here is to use some PyTorch notebook in which I'm doing some machine learning reconstruction of image for some zebras that are in some photos. They have been the quality of the image degraded, the resolution is decreased. So I want to reconstruct the image starting from my use dataset. And so I restart the kernel here, and this notebook use the GPU, which is available on the node on which I'm running. So in this case, I will restart the kernel, and since I'm using the GPU, we implemented also a plugin by NVIDIA, which allows you to monitor the GPU's usage on the fly. So in this case, I run the cells, and then if you click on this button, on this button that you will see here on the left in a while, you will see that you can monitor the GPU resources on the fly here. And basically, this can be very useful to understand when you are using, where you are having an optimal usage of the resources, if there is offload from the GPU on the GPU, from the GPU. You can see here the PCI throughput on the bottom. And here you can see the memory occupancy for the GPU. This is the GPU utilization, which is quite ugly actually if you have just one GPU, because the bar is very big, but in general it's more appealing from the aesthetical point of view. And this can be very useful, and something that you cannot perform very easily with a batch approach, traditional batch approach, because you cannot have at your disposal all these instruments that allows you to interact with a visual tool that is not normally available in the case of batch jobs. So let me go back to the slide, sorry. So this is the idea of the interactive computing approach in general. So this was the interface. Everything was running. Everything is running actually on the HPC cluster. And in particular, what I mean with the backend nodes is what we have seen here was related to backend nodes. Then actually, you saw what you see here is the fact that you are running on these nodes, but you can actually submit a job on the compute nodes that you see here on the Galileo 100 partition. And in order to do this with batch jobs, you can use a web interface which is called the Slurm Queue Manager, and I will show you in a while from a moment. And it's something that we added here in the bottom. It's the button that you see here on the bottom part of the. And from this part, basically, you can monitor all the queues which are on the Galileo 100 cluster, or in general on the cluster on which the service is deployed. And you can manage job notification, but you can also submit new jobs. and also kill the running jobs and whatever you want, basically whatever you can do with the Slarm on the cluster. Why do we care about this? Because basically in this way you can mix the approach that you have with the interactive computer, so web visualization and with the with the Jupyter interface, and maybe visualize the results that you obtained from web jobs. So it's something that allows you to mix the two approaches in a quite comfortable way, using just a web interface, a web browser. Everything is done via web browser. Actually, also in the case of the basic Jupyter Lab interface, if you need something more traditional, for instance, you have a terminal interface just inside your Jupyter interface. So in case you need to use something more traditional, you have a terminal and you can access it directly from the web browser, which is very comfortable if you need to do something, let's say, more traditional. So as I told you before, so everything here is actually running, in that case, is spawning some jobs from the backend nodes to the compute nodes of the cluster. And there are some other services that we added, which is actually related to the fact that there are some plugins. There is a plugin in particular which is called the Jupyter Server Proxy, which allows us to add basically every web service which is normally used via a TCP port. So for instance, in this case, I will show you VS Code interface that we installed. So VS Code, Visual Studio Code, which is a very common code editor that you probably already know. It's for VS Code is available web interface. So it's something that can be run inside the browser. So in this case, VS Code is running on the cluster. So you can compile your code on the cluster and write your code on the cluster, debug it on the cluster, and run it directly maybe from your Jupyter Lab interface. And you have seen there that you have seen here that you have a Visual Studio Code button here in the middle, and as soon as you click there, there will be another tab inside your browser that allows you to access to a web interface, and from this web interface you will access directly to the files that you have inside your own Graila 100. So what you see in the left here is my very messy home on the cluster. And if you go ahead, basically you can see that you have a quite common, let's say, Visual Studio Code interface, but directly without installing everything. Everything is done directly via web browser. So this is basically the core of the user experience that you would have with the IC implementation. So now actually, also everything is currently installed on Graila 100. This is not open to the public, not open to the public yet, just because we are waiting for the response for security assessments, and it finished last week. So we are going to open probably to the public to the next week. So you will be noticed via the Fenix channels and via the Fenix website. Hopefully the next week, or by the way, before the end of May. I'm quite sure about that, and we will open to the public the implementation which is on Graila 100. So this link is not accessible yet, but it will be in a very, very few days, hopefully. And the only requirements that you will have from your side is to have an active project at CINECA. This is the same approach, the same issue that you will have, the same requirement that you will have on the other Fenix implementations. In this implementation in particular, we will add also something more. You will see also some the Julia kernels and the RStudio, just like the RStudio interface, just like the Visual Studio Code interface that I showed you just right now. Probably also Octave, and mostly a VNC desktop, which can be run directly from the Jupyter Lab interface. So this is the basic idea for the IC implementation. But actually, there are some the other implementations that are in Fenix. A couple of them, in particular the ULIC one and the CSCS one, they are quite similar to the one which I've showed you so far, with some exception. And in particular, I will start from the interactive computing at JSC. Actually, just to be clear, there is if you go here in the Fenix website, you can have the links for all of them. So if you go into infrastructure, there is services here, and from services there is an interactive computing services page, from which you can see all the already publicly available services in the Fenix sites, and there will be also the CINECA one in a few days, hopefully. So we start from JSC1, and because the user experience, so the Jupyter, everything is based strongly relying on Jupyter, just like the implementation that I showed you so far. And there's a big difference actually, which is the fact that the spawner in this case is managed via, the spawning of the job is managed via Unicorn. And Unicorn is a tool which allows you to spawn the backend part not just on one single cluster, but actually on different clusters. So basically, the service has a front end, which is the same for every implementation, but actually the backend part can be running either on GWAS or any on HDFML or any other computational resources which is available at ULIC. So this is a different approach, which is a bit quite more flexible actually from the computational point of view with respect to the one that I showed you before. And because it basically spawns on every computational resources that is present in ULIC. So, and it actually is able to also to employ resources not only on the HPC cluster, but also on in theory on cloud systems using not Unicorn in that case, but an internal tool which is called User Lab Manager. So in these cases, if you have an active project at JSC, I strongly recommend you to visit this website, which is the same that you find in the web page that I showed you before here. And in this case, you will see also the documentation, which is quite deep. You will see here the details for the implementation, but you will see also the fact that there are some extensions installed, and there is also a very useful guide in order to easy the user to create their own environments. So in the case, this is the case of the JS implementation, whereas for CSCS, actually from the technical point of view, the user experience will be very, very similar to the one that I showed you in the IC implementation, because from the technical point of view, it's very, very similar to the whatever I've shown you before for CINECA's case. So actually, everything is running via Jupyter Lab on for the front end, spawned via Slarm on some backend nodes. In this case, the cluster used is PISDaint, and basically the situation is quite similar. So if you go to the documentation here, you will see that you have a sign-in page in which you can access either via your CSCS account or via your Fenix EDP account, or even via APH credentials. And actually, if you take a look to the documentation here, you can see actually that there is a quite useful documentation in order to make your experience easier. In particular, at CSCS, they made available some tools for the command line in order to create your own custom environments. And there is a module which is called the Jupyter Utils in order to let you create kernels in an easy way. And there is also Python package, Python module on which you can install via pip in order to use very easily an MPI implementation for your interactive computing session. So point is, so this is the most common, sorry, the most similar approaches to the one that I showed you before. So everything is strongly relying on Jupyter, both for CSCS and ULIC. Whereas in the case of CA and BSc, the approach is a bit different. In particular, in the case of BSc, everything is running on HSM cluster, and you can find the documentation for the cluster here. So if you go here in the web page that I showed you before, and here, sorry, you see the documentation here, and you will see that that with the usual approach that you have with Slarm, you can start an interactive session on a compute nodes. But from this interactive session on a compute node, you can actually start a Jupyter Hub session. But in order to do so, you actually, in order to have access to this HSM cluster, it's not sufficient just to have an account active on BSc, but actually you need also to communicate a public IP to be whitelisted for the access to HSM cluster. In this way, the Jupyter Hub server can be exposed, and you can access directly on the compute nodes using the node that you reserved for that you allocated via Slarm. Whereas the last implementation that I showed you is has something common with the one at BSc, the one at CA. I'm talking about one at CA because you start from the command line, also in this case. But in this case, you are not starting Jupyter Hub actually, but there is a service which is based on NiceDCP. NiceDCP is basically a remote desktop implementation. So you have a tool which is called NiceDSB, and you have a command line approach that you need to start with. So you need to access to the login nodes via SSH, and then there is a command here in the guide which is called CCVisu virtual, that allows you to start a NiceDCP session. In return from this command, basically you obtain a web URL. If you access from your browser to this web URL, you need to log again with your credentials. In this case, they are IRINI credentials because everything is running on the IRINI cluster from CEA. And if you access to this web interface, which you initialized from the command line, basically you have access to your remote desktop, which is a GNOME desktop in this case. Everything is running, by the way, inside your web browser. So basically, you once again, you don't need to install anything. Everything is done via web browser, but you need to start it from a command line also in this case. So it's something a bit different with respect to what we have seen before, but actually you can start if you need Jupyter inside the GNOME environment, or actually you can use any kind of graphical interface inside the environment that you started on the cluster. So also in this case, just like in the case of the other clusters, you need to have an active membership at CEA in order to access to this kind of service. So I think it's everything from my side. Sorry, I took a bit longer probably with respect to what I should have. And I'm here for any question. Thanks a lot for listening.
Thank you very much, Fabio. If someone have any question, please, you can leave it on the chat or in QA space. Is there a roadmap to include the eBrains kernels?
So there's a roadmap. Actually, there's not a roadmap, but we didn't plan it yet, but we discussed it in the last HPP summit. So we are working from two different sides. We are implementing the module in the cluster, which I think it's not in charge of me, so I don't know the details. But actually, I think it's either done or almost finished. Then, in order to add it in the interactive computing, we need to customize the buttons that you add. Basically, it's not very difficult to implement, but it needs to be tested. So I don't want to give you a timing because I don't know if I will be able to respect. But so that there's not a timeline, but actually it's something which is planned. I will not give you a timing, but it should be something which is coming, basically.
So he has another question here, a comment. At CSCS, maybe also JSC, I can spin up a Dask cluster with example 30 nodes without too much delay. Can this be done here with the Slurm pass through to the compute nodes?
I mean, in theory, you could. In practice, there are no 30 nodes, you said, which is more than the one that will be available, actually. And actually, the limit of partition will be smaller. So from the technical point of view, you could, in theory. In practice, in the specific implementation at CINECA, there will be not enough resources. But I think that the problem you had with Dask is quite common in the case of Dask because it doesn't scale up in some specific cases. If you not so sure that you can consider in this case the Slarm implementation as an alternative to the Dask one. I mean, if you are able to rewrite your code without using Dask, basically you can try to use a different approach, like, I don't know, MPI for Pi or whatever you want, and allocate as many resources as you want. Maybe you don't have the issue, but in general, in the specific CINECA implementation, there will be not enough nodes to reach the same amount of simulation. But in theory, you could, from the technical point of view.
Sorry, Fabio. No, he mentioned something like, I mean, using the other computing nodes.
But the other computing nodes that you, if you are talking about the CINECA implementation, the other computing nodes, they are only available for bad jobs. So if you submit a bad jobs from the web interface, then yes, you can basically submit whatever you want for, I don't know, also, I don't know, 100 nodes if you need. And then you can interact with the results that you obtained via the interactive community. In that case, you can do it, but it's something in the middle with respect to what you will do with a single notebook. So in that case, I mean, you need to submit something, then you need to analyze the data that on which you use Dask from the interactive computing web interface. Don't know if I replied actually because. Okay, now I see the Dask distributed allows to use Slarm to spin up the workers with Slarm. I guess you could. There should be an environment which contains all the dependencies of. There is actually one Dask implementation. We didn't try to exploit it so much, but in theory, it's something that could be explored in order to, if you have. Not so sure that actually, in this case, you will see the difference because in this case you have Dask running inside a Slarm implementation, which is not seen from the Jupyter notebook. I mean, Jupyter basically doesn't know that it's running inside Slarm, so it's not running a Slarm by itself. It's running inside Slarm. So I'm not so sure that is the case, but maybe I didn't get exactly your point, so maybe I'm missing something. Yeah, there are no networking. I mean, no more than any other compute nodes and so on the cluster. It's just like the same. They are exactly the same nodes that you find on the cluster. So if you have the same issue on the compute nodes, you have basically the same issue here. There are no network barriers specifically for this implementation. There's no difference with respect to the compute nodes of the cluster. So each nodes can talk to each other one. Sorry, Jan, I see now that actually you, in the beginning, you were referring to the CSCS implementation, not to the CINECA's one. So in this case, I guess it's the same actually, but maybe in that case, it's better if you ask to CSCS support them. So maybe they know better if there are some different implementation about the network or about the environments that they created. In the case of CINECA's and the IC implementation, I don't see any particular issue, but for CSCS, I think it's the same for CSCS, but maybe it's better if you ask to their support.
I'm already doing that at CSCS.
Okay.
I want to know if I can do the same at CINECA.
I will check the documentation that you sent. I think it's basically just like the same. So if you are doing it CSCS, I don't expect any difference. But if you want, you can check together if you want to try. As soon as it will be open in production, if you want to, feel free to contact me and we can also take a look together.
Thank you, Jan, for your questions. Thank you, Fabio. So no more questions. So I'd like to say thank you for all of you that will be was with us during this hour, more or less. And we appreciate if you can respond our survey. I shared with you a link in the chat. And you will receive an email with the survey too. It really help us to understand your needs. So thank you very much. And if you still have any questions or if you want to reach us, please contact us by website, by email, or social media. We are happy to respond to your questions and listen your comments. Thank you very much, Fabio, for your time and hope to see you soon.
Thank you, Luciana. Bye.
Thank
Bye.
you.
Thank you, everyone.
Bye.